Warning! The video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. In this video, we're going to continue our discussion about tangent lines and how they relate to derivatives. So we haven't really mentioned a derivative yet, but at least we can start talking and really investigating slopes of tangent lines and recalling them. So if you have gone through a calculus course so far in the order that the material is presented traditionally, you have already seen this topic. So this is just kind of a recall of an old topic. So in this example, we're asked to find the slope of the tangent line at the point 1, 0 using quote unquote both definitions. Now, what do I mean by both definitions? Well, in the previous video, we saw that we had this one definition right here. I'll highlight it, the full thing. We have that one definition, but there's the secondary definition down here. So we're just going to find the slope of the tangent line using both of those, just to see which one works better, if there is one that works better. So let's start there. The function we're given, by the way, is f of x equals x minus x cubed. So let's start with the limit, and let me zoom in because it's a little bit cleaner, as x approaches a. And by the way, did they tell us? Oh yeah, they did. They told us find the slope of the tangent line at 1, 0. That means at x equals 1. So rather than allowing x to approach a, I'm just going to make a note here that a is equal to 1. So we're allowing x to approach 1. And it's going to be just using the formal definition of the slope of the tangent line. It's f of x minus f of 1 over x minus 1. It's just the slope of the line connecting 1 comma f of 1 to x comma f of x. And you're allowing x to approach 1. Again, you would want to initially, now that we have limits behind us, we know how to deal with limits, you would want to try direct substitution, but we cannot use that here because it would cause division by 0. So we immediately know that direct substitution's out of the realm of possibility right now. Then I'm going to take f of x, which is x minus x cubed. Let me insert that in here. X minus x cubed. And then we're going to subtract f evaluated at 1. And if you plug 1 into our function f, you'll get an output of 0. So I'm just going to write minus 0. Still all over x minus 1. Obviously, the minus 0 doesn't matter, so I just erase that, and I kind of clean this up a little bit. By power of whiteboard is what I would normally tell my students. And still, plugging 1 in is not going to work, so we're going to do a little bit of algebraic cleanup. As I mentioned over and over, always perform arithmetic before algebra, algebra before trig, and trig before precalculus, and precalculus before calculus. Basically, climb that ladder of mathematics. So in this case, I know that I could factor. I'll factor an x out of that numerator, and I'm left with an 1 minus x squared. Again, I can't do direct substitution because I have division by 0. So I guess I should do a little bit more algebra. Limit as x approaches 1 of x times 1 minus x times 1 plus x, because that's a difference of squares, over x minus 1. And you either know this or you don't, but you can cancel, in a way, the 1 minus x and the x minus 1 if you recognize that you would have been able to factor a negative out. If you don't know what I just said, I will say it this way. Factor a negative out of that factor of 1 minus x. So if I do that, I'll get a negative limit as x approaches 1 of x times x minus 1 now, x plus 1, all over x minus 1. sign swap on the 1 minus x to be a x minus 1. And now you see that there is a clean algebraic move to cancel the x minus 1 factors. If you want to be rigorous, mathematically rigorous, you would say, I am dividing both numerator and denominator by x minus 1. And at that point, you can use direct substitution. I use the quick notation ds for direct substitution. I allow x to equal 1, and you will get negative 1 times 1 plus 1, or negative 2. And so that is using the first definition of the slope of the tangent line. The second definition, because we're asked to do both, is the following. It is the limit, so I'll write or. We could have taken the limit as h approaches 0 of f of a plus h minus f of a all over h. But in this case, remember, a, our anchor point, what we're approaching, or basically the point of interest, the x value of interest, is 1. So I'm just going to go through these and erase the a's and replace them with the number 1. And then we'll evaluate that. By the way, again, cannot use direct substitution initially because that would cause division by 0. So take this limit as h approaches 0. We'll have an h in the denominator. In the numerator, you're going to evaluate your function at 1 plus h. Turn that off. Sorry about that. It's my phone. All right. And so plugging in 1 plus h into the function, we get the following. It's a 1 plus h to the first plus 1 plus h being cubed. Let me just double check that that is correct. Nope, it was a minus. That's why I double check. So it was x minus x cubed, so it's 1 plus h minus 1 plus h cubed. And we're going to subtract from that, and be very careful with a subtraction like this. So this is kind of the bad thing about evaluating like this, is that you can really have problems. I see this a lot with students when they're using like limits and difference quotients, is that their subtractions, they forget to subtract off everything. So I'm going to write this out kind of slowly just to showcase what I mean. So you evaluate f at 1. Yes, it's totally easy just to plug 1 in, you get 0. But if you didn't do that and you wrote it as 1 minus 1, because 1 minus 1 cubed, you want to make sure that you're subtracting that entire statement. If you wrote it this way, it would be totally wrong. So I'm just kind of reminding you that when you have subtraction, that subtraction is subtracting everything to the right of it. So be very careful of that. But since this is 0, I don't really have to worry about that. I'm just going to erase it and also fix my fraction bar there because it's mighty large for not needing to be. At this point, again, you cannot allow h to be 0 because you would end up dividing by 0. So instead, you distribute. So you have the limit as h approaches 0. Remember, algebra before everything else, except for arithmetic. And so you have 1 plus h, and then this piece right here, you're going to subtract that. You know that that is 1 plus h plus 3h squared plus h cubed. You know that from Pascal's triangle, or the binomial expansion, which is a prerequisite for calculus. It's from your pre-calculus course. If you have a question on that, you could always ask it, and I might make a video on it, or if you're one of my students, I could talk about it in office hours. But I happen to know that's what that's going to turn into, and we're subtracting that entire statement, so it's actually a minus 1 minus 3h minus 3h squared, and then finally minus h cubed. I have to kind of grow that fraction bar a little bit. Still, I cannot allow h to be 0, but I sure can cancel like terms in the numerator. Let's see. So what do we end up with? Let's It's the limit as h approaches 0. Again, that denominator is just a little h. We have h minus 3h, or a negative 2h in the numerator, minus 3h squared, and then finally minus h cubed. Notice that each of the terms in the numerator have an h in common, so you would factor those out. They would cancel with the denominator, and I'll go ahead and write that, but I think you're at a level now where you don't really need to write every little algebraic step, but that's okay. I'll just showcase my work here, make sure that everybody is okay with it. Let me double check, make sure I didn't make any mistakes, which I'm prone to, by the way, if you know me. The h's cancel beautifully. And now I can just do direct substitution because it no longer causes division by 0. So if I allow h to be 0, this will end up being negative 2 because all of these other terms tend to 0. Now I want to pause to really get your attention here. Oh, by the way, I didn't write down that this was direct substitution. Let me go ahead and do that. Direct substitution. All right. So I want you to pay attention to something that's kind of important here. You have two methods or two limits that you can use to find the slope of the tangent line at a point. It is completely your option which one you want to use. And if you look at both these limits and the work involved, a lot of students will say, I prefer the first one. I'm not one of those. I actually prefer the second, and most of the time you're going to be working with the second definition. So they both have their use cases, but the second definition is kind of the more useful of the two. However, I will say when working with polynomials, I think that first one is pretty solid when working with polynomials. When working with everything else, it's not that great, but polynomials, it's pretty decent actually. So part A is done. Check, check. Now let's go ahead and do our algebra. The algebra is just find the equation of the tangent line. And this is a very common question in calculus. So if you're really good with your algebra, then you're going to love this part of calculus because you're constantly asked for the equation of a tangent line. Remember, a line, whether it's a tangent line or not, has two things, a slope and a point. That's all you need to find the equation of a line. So I just need a slope and a point. I'm going to write that down. So we need a slope and a point. Well, luckily, in this problem, they've given us a point. They've said, find the slope of the tangent line at this point. So I already know the point is going to be 1, 0. And the slope of the tangent line is, the slope of the tangent line is what we just found, right? It's a negative 2. So we have our slope, we have our point. So the equation of the tangent line is the line having the slope negative 2 going through 1, 0. And we could just use the point slope form of a line, which is this, just to remind you. This will probably be the first and last time I ever write that for a calculus class, but there you have it. So this will imply that you have y minus 0 is equal to a negative 2 times x minus 1. Don't leave it like that. You should put it in slope-intercept form. So I'll just leave it like that, and I'll box that up. Now, the slope-intercept form it just depends on your instructor. Some instructors are okay with you leaving your equations in point-slope form. That's point-slope form right there. And this one is slope-intercept form. Some instructors are totally fine with you leaving your work in point-slope form. However, not all of them are. So just get used to moving things into slope-intercept form. It's a more useful form in a lot of situations. Although I have to admit, the point-slope form is really nice to deal with. But I'm trying to prep you for anybody. And then finally, the last piece here just says, use Desmos to show the curve and the tangent line. And luckily, I actually can just reuse a Desmos applet that I created a few minutes ago. So let's go ahead and do that. Now this is the Desmos program I created a few moments ago for a different lecture. I'm just going to remove all of this. This is my function. I'm going to replace with x minus x cubed. I want to show you how to create your own applet, essentially, or your own Desmos graph. So the black curve there is x minus x cubed, a pretty beautiful curve. And our anchor point, a comma f of a, is actually at 1. So I'm going to change this a value right here. I'm going to change that to be a of 1. And then all we want is our x values, which I call b comma f of b in this situation. I want to allow those to get closer and closer to x equals 1. Now, obviously, I can't allow it to become 1 because, again, if I allow it to become 1, we have both division by 0 and the numerator is 0 for the slope formula, which, by the way, if you notice right here, I've actually written out, this is how I'm graphing that tangent line. I actually wrote out the equation of a tangent line. It's y minus y1, where y1 is f of a, times the slope. You can see that's the slope formula, f of b minus f of a over b minus a, times x minus x1. Well, x1 is a, y1 is f of a. So that's all I did. I just really created like a dummy little formula there. I want to change this b. Actually, I'm just going to change this b to go from, let's say, 0 to 2 in step sizes of 0.001 or something like that. Just so that we can really see a smooth curve, right? So there's a secant line, and then it eventually gets very, very close to our tangent line. I'm going to zoom in on that so you can see it. That's a super good approximation of our tangent line to this curve. And that's the idea. You're just dragging a point to that value. If you're wondering about the a comma f of a business, or I should say a plus h comma f of a plus h business, it's the same idea. You have a point, an anchor point, a comma f of a. It's at x equals 1. That's all we're concerned about. And then you have another point that's wiggled only slightly away, a plus h, right? That h is the wiggle, and if you look, I relabeled this over to our left-hand side here to be h. You could drag that h to get closer and closer to 0. As you do that, that green point gets closer to our red anchor point. Now it's almost identically at our anchor point, and that gives us a great view of the tangent line. By the way, h does not need to be positive. It could be negative. I could allow h to go backwards to negative 0.31 or whatever it is. It just means that you have your wiggle is a negative wiggle. You're looking in the other direction to connect 2 points together. So I'm just allowing h to approach 0 again, and we're fine. That's how it works.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.